Moving electrons create magnetic fields, and in magnets, it's going to go away from north and towards south. So the direction of current will do this. Okay, so for the curved right-hand rule, your thumb is going to go in the direction of the current, which is this way. And then your fingers are going to curve towards the magnetic field. So if it's going into the page, you'll curve this way. Okay, so for the flat right-hand rule, your thumb is going to go in the direction of the velocity, and your fingers are going to be the magnetic field. And then once that's all set up, you will be able to determine the force. So your fingers are going to go into the page in this one, and your thumb's going to point in the direction of the velocity. And in that case, then the force is going to go down. When the magnetic fields and the velocities are going in the same direction, then there's no force. And the same thing is when same thing happens when there's no movement also. So then there'd be no force. Okay, so here's some problems for magnetism. And for magnetic force on charged particles, you use this equation, where Q is the charge in coulombs, and then V is velocity, B is magnetic field, and then sine theta is between B and V. And then this equation here is magnetic force on current carrying a wire. And then same thing applies, V is magnetic field, I is current, L is length, sine theta is between B and I. And then over here is magnetic field from a current carrying a wire, and mu is actually constant, where mu is 4 pi times 10 to the negative 9th, and I is current, 2 pi, R is radius, and then velocity in an electric and a magnetic field is this equation.
This is a cross E and B field, E being the electric field and B being a magnetic field. So, if an electric field and magnetic field are 90 degrees from each other, the magnetic force and the electric force cancel out, allowing any particle to pass right through at any velocity. So, since electric field and magnetic field are equals, you can set the equations equal to each other in order to find the equation E equals E over B to find the velocity of the particle. Whenever a particle is in magnetic field, if the force that you find using your right-hand rule is 90 degrees to the velocity, the particle will have a circular path because of the centripetal force that is being created. So in order to find the radius, you have to set magnetic field equal to circular motion to get your V's cancel out, and you get an equation for radius, R equals mv over qb. To determine the path that a particle will take in a magnetic field, we know that if the velocity of the particle is parallel to the magnetic field, there will be a constant v. We know that if the force is perpendicular to the velocity, the particle will have a circular path. But whenever a particle is not perpendicular or not parallel, whenever it's anywhere in between, if there is a part of the velocity that is going perpendicular to the magnetic field and a part that is going parallel, because the velocity that is parallel is constant, the particle will move in a helical path in the magnetic field.
Electromagnetic induction is any change in magnetic field through a closed loop of conductors creates a current. Magnetic flux is the amount of magnetic field going through a given area. And in this equation, magnetic flux is this thing. And then this is magnetic field, and this is area. And then cosine theta is the angle between B, which is magnetic field, and the line drawn perpendicular to A, being the area. Changing flux creates current by creating voltage. And then in this equation, voltage created is in volts, and then the negative change in flux is over the change in time.
These are the steps to solving an induced current problem. So first off, we need to find the change in the problem. So take this problem for example. This wall is moving to the left, which is causing us to have less and less x's, or magnetic current going into the page. Second, you need to oppose the change. So right here, so our change, we're having less x. So to resist less x, you need more x's. So, or vice versa, if you were, had less dots, you need more dots, or magnetic field coming out of the page. If you have more X's, you need more dots. If you have more dots, you need more X's. Last thing you need to do is use the right-hand rule to find the current of the problem. So, we have our box, so we need more X's. So that's magnetic field going into the page. So if your thumb is the current, you need to put your thumb towards the page, and your fingers wrap around, causing you to have a current that goes around clockwise around the problem. And that's how you find the current for an induced current problem. Okay, this is the all or nothing quiz problem for Unit 8 magnetism. So, problem is, in region 1 shown above, there is a potential difference of 5 volts between two large parallel plates separated by a distance 0.1 meters. In region 2, to the right of plate D, there is a uniform magnetic field of 10 Tesla pointing perpendicularly out of the paper. An electron with a charge of negative 1.6 times 10 to the negative 19 power and a mass of 9.11 times 10 to the negative 31st power is released from rest at plate C as shown and passes through a hole in plate D into region 2. Neglect gravity. So, first off, we need to point out what we know in the problem. So we know that there's a potential difference of 5 volts. So, 5 volts. And there's the distance of 0.1 meters. The electron has a charge of negative 1.6 times 10 to the negative 19. And it also has a charge of 9.11 times 10 to the negative 31st. We also need to know that the magnetic field has a charge of 10 Tesla.
Okay, so we want to find the speed V0, V0 of the electron as it exits the hole. So we start out with conservation of energy to find that. So E equals E prime, and it starts out as electric energy, which is QV. Your charge Q times your electric potential V, and that equals to your kinetic energy, which is 1/2 mv squared. And that is what we want to find. So then we can plug in our values. So 1.6 times 10 to the negative 19. Use the magnitude, not the negative value. And then you multiply that by the electric potential, which is 5 volts. And that equals to 1/2 times your mass, which is 9.11 times 10 to the negative 31st. And that's multiplied by V squared. So then you can plug that into your calculator, and then we get that V squared equals to 1.7563 times 10 to the negative 31st, times 10 to the 12th. And then you take the square root of both sides. And you get that V equals 1.33 times 10 to the 6th. And that's in meters per second. Okay, so this problem is a 3-part problem. And first we need to find electric field, E, and that translates into electric force, which is F of E, and then we use that to find the acceleration A. So first of all, when we want to find electric field, we use the formula E equals V over D. And then since we've all probably forgotten that, how you derive this formula is from electric potential and electric field. So we know that electric potential is V equals KQ over R, and then electric field is KQ over R squared. So So when you take electric field and you multiply both sides by R, you get that E times R equals KQ over R. And R is your distance, which will turn into D. So we get that E times the distance R equals KQ over R, which is the same as your electric potential. So then when we solve for that, we get that electric field equals to electric potential V over R, or V over D. Okay, so now that we found this formula, we can plug in the numbers for it. So electric field equals electric potential, which is 5 volts, over your distance, which is 0.1 meters. So then you get that the electric field equals 50 newtons per coulomb. That's just the units for it. Okay, so now we go to the next step of the problem, which is to find the electric force. So we use the formula F equals EQ. And then F is the electric force, E is the electric field, and Q is your charge. So we get that the electric force equals 50 newtons per coulomb, right there, times the charge, which is 1.6 times 10 to the negative 19th. And then we get that it equals 8 times 10 to the negative 18th newtons. Okay, and then now that we found that force, we can use that to find acceleration, which we get from sigma F equals ma. So your force in this is that 8 times 10 to the negative 18th. And then use your mass, which is 9.11 times 10 to the negative 31st. And that's multiplied by acceleration. So then you divide both sides by that, and then you get that acceleration equals 8.78 times 10 to the 12 meters per second squared.
Okay, so next part of this problem, so we have to draw and label an arrow to indicate the direction of the magnetic force of the electron as it enters the constant magnetic field. Okay, well first off, we have to recognize that since our particle is an electron, we have to use the left-hand rule due to the electron having a negative charge. So, next, so we can find the arrows and indicate the direction. We have to figure out which way velocity is going. So, since the electron moved from region 1 to region 2 towards the right, velocity is going towards the right. And since our magnetic field is has a circle, that means it is going out of the page. Okay, so we need to take our left hand. So, magnetic field is going out of the page. So now our fingers are going to be pointing out. Next, we need to find our velocity. Our velocity is going to the right, so our thumb has to be going to the right. Now, since our palm is the magnetic force is going up, and electric force is equal and opposite to magnetic force, so it's going to be going down. Okay, so now that we found all of our forces, we have to draw them. So, our arrows, our magnetic force, like we said, is our palm, and that is going to be going up. And since electric force is equal and opposite to magnetic force, it will be going straight down. Okay, and there's a special rule that says if the magnetic force is 90 degrees, is perpendicular to the velocity, the particle will move in a circular path towards the magnetic force due to centripetal force being created. So our electron will have a circular path towards the magnetic force in region 2.
Okay, the next part is to find the radius r of the circle. And we know that this particle starts out with magnetic force, which is F of B, and then that converts to centripetal force, which is F of C. Okay, so magnetic force is QBB, which is your charge times your velocity, and then times the magnetic field, B, and that equals to mv squared over r, which is centripetal force. So we can cancel some things out, the v's on both sides, and then we solve for r, so we can get that r equals mv over qb. So now we can just plug some numbers in. So m is the mass, which is 9.11 times 10 to the negative 31st kilograms. And multiply that by the velocity that we found in the first part, which is 1.33 times 10 to the 6th meters per second. And that's over Q, the charge, which is 1.6 times 10 to the negative 19. And then times 10. And that's our magnetic field in Teslas. And then you plug that all into your calculator, and we get that the radius r of the circle is 7.57 times 10 to the negative 7. And that's meters.
Okay, the last part of this problem is to find the electric field that would be necessary to cause the electron to continue on a constant V inside the magnetic field. So first we have to set electric force and magnetic force equal to each other because they're equal and opposite, like I showed you above in finding the path of the electron particle. So let's do. We have to set EQ equals QVB. E is the electric field, Q is charge, velocity, V is velocity, and B is magnetic field. So our Q's cancel out, and we're left with E equals VB. And now we just plug in using numbers from earlier on in the problem. So our V is what we found in part A, which is 1.33 times 10 to the 6th. And then our magnetic field is 10 Tesla, like in the problem. And then our answer comes out to be 1.33 times 10 to the 7th newtons per coulomb. And our direction would be up, because as I showed you in the graph, the particle's path was an up circular motion, so the motion will be going up.